released every day by Yuan Spence, and I'll just let him continue with his talk.
Okay. Hello, everyone. Good morning. Summer school. Right. Let's recap.
Oh, I'm sorry.
Oh, yeah.
Yeah. Okay.
So good. Can you hear me okay?
Yeah. Yes.
Okay. So I'm going to do now on this first slide a recap of what we did yesterday. But then I want to emphasize, if there are any questions, then once I've given this recap, perhaps that's a good opportunity to ask them. So yesterday I said we're studying this model problem. Got my pen in the wrong mode here. We're studying this.
Sorry. You need to share. Can you share your screen? You're not sharing your screen.
Well, I'm sharing the iPad. Yeah, can you see my screen now?
Yeah. Now we can, yeah.
Okay. So we're studying this model problem of the Helmholtz equation, just constant coefficient Helmholtz equation in free space in RD, plus this radiation condition, which physically corresponded to the condition that the waves are generated by the source and travel outwards. And we reformulated it as this variational problem. So we did exactly what we normally do to find the variational formulation of say a second order linear elliptic PDE. We multiply by a test function and integrate it by parts. So we're in the energy space H1, but the only difference between this and finding variational formulations of second order linear elliptic PDEs that you will see before is that now we're on this ball of radius r, some arbitrary r that's big enough to contain the support of F. And then this sesquilinear form then involves this exact Dirichlet-Neumann map for the Helmholtz equation in the exterior of this ball of radius r. And we're doing all this because the solution U to this problem is not in H1 of RD, right? That's the subtlety. Right, so here's the sesquilinear form I'm just reminding ourselves of. This is this DTN map. And so we're treating this Dirichlet-Neumann map as known. Of course, we can write it down in terms of Fourier series by separation of variables. We're treating it as known. I should mention there are more sophisticated ways to deal with this kind of outgoing condition, such as perfectly matched layers. So I know some people in the audience will know about these. And actually that was what this paper that was posted on the archive yesterday dealt with. It was proving the analog of the results I'm going to prove to you today and tomorrow. But when instead of using this exact Dirichlet-Neumann map truncation, we use perfectly matched layers. So here's our yellow box, the orders where the instructions we're following. Find the U in H1 of this ball of radius r such that AUV is f of v for all v in H1. And we want to compute a solution, or compute an approximation to the solution of this using the Galerkin method. So in this method, we're given some finite dimensional subspace of H1. I'm calling this finite dimensional subspace calligraphic H sub n. Can think of, say, the n as the dimension, finite dimension. And then we repeat our instructions in this yellow box, but we replace the Hilbert space H1 by the finite dimensional subspace. And so this has got to hold now for all Vn in Hn. Right, and so that's the sort of beauty, or the why this Galerkin method is the the popularity or the applicability of it is because it's so closely, so closely related to this. It's based on, in fact, the variational formulation of the PDE problem, right? Which means it's very easy then to use information on the PDE to analyze the Galerkin method. Right, and I said last time we were thinking of this HN. Really, we're going to have a sort of sequence of these. These are piecewise polynomial subspace, right? So I divide my domain, chop it into lots of little pieces of mesh width h, and I approximate on each piece the solution by a polynomial of degree p. And the goal, we said the goal was find conditions on h and p such that we have quasi-optimality, right? So the error in approximating u by this Galerkin solution un is up to some constant CQO that is independent of k. The error is up to some constant, the smallest error one can hope for in approximating the solution by elements of this subspace HN. Okay, and so here I'm working at H1. I put this subscript k to remind ourselves that I'm weighting each derivative with a power of k inverse. And I'm not gonna, so I'm working on H1 of the ball of radius r, but just to save some writing, I'm not gonna write that all the time. So I'm just gonna write H1. Yeah, and remember this was quasi-optimality. Optimality up to this constant CQO. And what I said that the sharp results, so two sharp results that in fact we're going to prove, is that when p is 1, the condition hk squared sufficiently small ensures this. So k independent quasi-optimality, but then, so that's one case. And the other case is this case then proved by Mellink and Zauter in 2010, that if hk over p is sufficiently small and p grows, or p is bigger than a constant times log k, then I have this k independent quasi-optimality. So this second one here is Mellink and Zauter 2010. And I said last time that with this, if I choose h and p so that these inequalities hold with equality, then the total number of degrees of freedom grows like k to the d, right? So this is important. So let's just say again, the total number of degrees of freedom goes like p over h to the d. And so in this second case here, if these inequalities hold with equality, the total number of degrees of freedom goes like k to the d, which is this natural threshold for approximating an oscillatory function. So that's the significance of that result. And now let's then have here this information. I said at the end there was this information about A and the solution operator that we're going to carry with us. So the information is that A, the sesquilinear form, is continuous. We're going to need that. So there's a C cont independent of K, such that AUV is bounded by C cont, then the H1 K norms of U and V. And then we had this Gordian inequality that the real part of AVV is bounded below by the H1 K norm squared minus then some L2 term. And finally, then I said we're going to use this bound, this a priori bound on the solution, that in fact the H2 norm of the solution, again using these weighted spaces, is bounded by C, a constant, times KR times then F in L2. Okay, and of course I'm talking about, I was saying I'm analyzing this problem in the limit k increases, but strictly speaking, it's kr that is this dimensionless quantity, right? So I'm often a bit sloppy when I say, okay, as k gets larger, but at least the bounds I write are going to have this dimensionless quantity kr in them. Okay, so my first question to you all is a cosmetic, a trivial one, is that I'm writing in different colors here, but are the colors all displayed okay on the screen? Like, are there any colors I should avoid?
Yeah, we can see them.
You can see them all? Okay, good. So that was the warm-up question to get you talking. The second question is, has anyone got any questions about this material just recapped here?
No, I think we're okay. No.
You're okay, good. I'm going to put some fancy box around this just to say that this is the sort of exciting thing we're going to try and prove using, well, we're going to try and prove using these elementary arguments. Right. So we want to find conditions such that this quasi-optimality holds. Okay. And first, and we've got our sesquilinear form A satisfying this continuity, and then this Gaudian inequality. So what we're going to do first is a warm-up. We're going to find or show that quasi-optimality holds when the sesquilinear form A is continuous and coercive. So this is a stronger property than the Gaudian inequality. Let me tell you what I mean by coercive. I mean that the modulus of AVV is bounded below by some constant, let's say C coer times V in, let's say, so here I'm writing the H1K norm, although actually these arguments I'm giving you are just valid in then any Hilbert space. Okay, well, so later we're going to, our Hilbert space is H1, and so I'm going to write them in this norm, but this, like I say, these arguments are more general. And of course, I'm sure, I know Kirill at least and other people, you'll all be familiar with problems like this. So so the Poisson's equation on some bounded domain is then the variation formulation of this is continuous and coercive in the H1 norm. Okay, if I got a Dirichlet boundary condition, I have then the H1 norm, and my space is H1 0 with a 0 trace on the boundary. Right. So the Helmholtz problem. I mean, one reason, or perhaps the reason on a PDE level, why the Helmholtz equation is more difficult than Laplace's equation, Poisson's equation, is because I don't have this coercivity, right? I have this Gaudian inequality instead, right? That's but let's assume we have coercivity and see how to get now this quasi-optimality. Okay. So the first thing we're going to do is we're going to note something which is called Galerkin orthogonality. Okay, so here is this variational problem, right? Find U in the space such that AUV is f of V for all V in my space. Okay, it's H1. And my Galerkin solution UN is defined as the solution, if it exists, of this equation here, right? Find UN in the space, in the finite dimensional space, such that AUN VN is f of VN for all VN in my finite dimensional space. So now, in the first equation, I can certainly let Vn, so V be Vn, right? Because my space Hn is contained in H1. And now I subtract these two equations, and I get then A U minus UN paired with Vn. So A, first argument U minus UN, second argument Vn, is 0 for all Vn. Okay, and so this is called Galerkin orthogonality because in fact in this coercive case, well, if A is symmetric, in fact, then A is actually an inner product, and this is saying that the Galerkin error is then orthogonal to everything in that inner product, is orthogonal to everything in this space Hn. Okay. So let's prove now under this coercivity condition that we have quasi-optimality. Okay, so quasi-optimality, so first, the Galerkin solution exists thanks to the Lax-Milgram theorem, right? The Lax-Milgram theorem gives you existence of a solution of your variational problem under coercivity, and somehow the same argument now works, just working in a finite dimensional space Hn rather than H1. So UN exists by Lax-Milgram, so we're okay to write things down involving UN. And now, thanks to coercivity, we have C coer U minus UN squared in H1 is bounded above now by A U minus UN, U minus UN. Right, so I've just taken the definition of coercivity and I've applied it with the specific function V being U minus UN. And I know that UN exists, so this is legal. Now, what else can I do? Well, I can use this Galerkin orthogonality, right? So let's just write here by coercivity. I want to write it. In fact, I don't want to write it, but I'm just so you remember this is by coercivity. Now I use Galerkin orthogonality, because my first argument is now U minus UN, so I can add to the second argument any element of the finite dimensional space, right? So I'm going to add the element UN minus Vn. I'm going to change this to UN to U minus Vn, and this is for all Vn in the space Hn. Sorry, I got reading this wrong. Right? This is since UN minus Vn is in Hn. Kirill, are you with me?
Yes, yeah.
Good. Good. This is just some proof by intimidation technique.
Yeah, but you showed us how it works under the assumption that we don't have.
Yeah, but don't worry, Kirill. Don't worry. It's hot here, but it's not too hot. I'm still in control. I've got a plan. Okay. Now I use continuity of A to bound A U minus UN U minus Vn by the norms of the argument. And okay, then this is still valid for all Vn in Hn. Okay, and this is good now because I just divide by one factor here, and I get exactly, and I divide by C coer, and I get now this quasi-optimality, right? Quasi-optimality bounds this Galerkin error by a constant. Okay, here it is. Then U minus Vn, and this was all proved by some arbitrary for an arbitrary Vn, and so therefore that is somehow, so I can choose the Vn such that this is minimized, and then we have quasi-optimality. Okay, and so this argument is called Sayer's lemma for the numerical analysis aficionados amongst you. Right, so as Kirill said, this is, we've proved now quasi-optimality, but under an assumption that we don't have, right? So now we haven't got coercivity, we've got our Gordian inequality. Okay, so now I'm going to go through the same argument but in red pen I'm going to make the changes where we have our Gordian inequality. Okay, so remember here's our Gordian inequality. Let me highlight it. Okay, so here now, so in the Gordian inequality, I just had a constant 1 here. I had now plus 2 U minus UN squared L2. Okay, and similarly, I had now plus 2 U minus UN squared L2. Okay, plus 2 U minus UN squared L2. Okay, so now, what I need is or I would like to show that U minus UN in L2 is smaller than, let's say, a half u minus un in now this h1k norm. Because if I can do that, then it means I can take this fellow here and absorb them into the left-hand side. Do you agree, Stephen? So
yes, I agree.
So it's okay. So there's this constant half, but to just, you know, if so, it turns out that's okay. But you know, if this is sufficiently small with respect to that, I can take it on the left and absorb it. Okay, good. So, like, unfortunately, Stephen and Kirill, since you're the only two people I know, you know that once I've asked one of you something, the next person is next, right? So Kirill, you've got to be concentrating now for this next sort of slide, because I'm going to be asking you, you know. Okay. In fact, I should look at the participants list, right, and see, you know, who else is giving courses, and I can then.
You can ask Igor. He's just behind me.
Igor, right, yeah, I saw he's on the participant list. Okay. Okay, so in this case, okay, this C co-error is just 1. So if I have this bound saying that the L2 norm of the Galerkin error is sort of small enough compared to the H1 norm of the Galerkin error, then I'm going to get this quasi-optimality. And let's just check. We said C cont, this continuity constant, was independent of K. And okay, that's what we want, right? We want quasi-optimality with this constant independent of K, right? That's our goal, I said here, right? We want this thing here, constant independent of K. Right, so we've reduced our problem to proving this bound here. So now the next slide is called how to get sufficient condition for this bound here. Okay, and in fact, this is a classic argument in numerical analysis. It's called the Orban-Nietzsche trick in the sort of Laplace equation case when it's coercive. And in this sort of Helmholtz equation setup, it goes back to Schatz in 1974. Right. So let's now start with a definition. So given an f in L2, I'm going to let S star f in H1 be the solution of A V S star f equals V F L2 for all V in H1. Right, so this is a variational problem, but now my unknown is appearing in the second argument of A, not the first. Okay, so this S star f is the solution of the adjoint Helmholtz, you know, it's the adjoint solution for this particular class of L2 data. Okay, so that's why I put the star, because it's kind of, if S is the solution operator, S star is then adjoint. Okay. So now, what are solutions of this adjoint sesquilinear form? Well, it turns out they're just complex conjugates of solutions of the regular variational problem. Because this lemma is saying, I'm going to write down now, says that S star f also solves this variational problem here. Okay, and so to prove that, I need some property of the sesquilinear form A, and for the bit of A involving the grad U and U in the domain, that's kind of easy, but I need some relation to do with the Dirichlet-Neumann map that you can kind of prove using Green's second identity and the radiation condition. So you can look at the details of that in the paper. But so the point is that the solutions of the adjoint equations are just complex conjugates of regular Helmholtz solutions. Okay. So of course you might be thinking, well, Ewan, if they're just complex conjugates of regular Helmholtz solutions, why are you bothering to introduce them? but we'll see that it's helpful to have this adjoint notation where when we're going to prove this bound here. Right. So now we have the lemma. I guess the lemma, it could be a theorem. It's going to be the thing that establishes this. Okay, so if a certain quantity that I'm going to call eta of Hn, so this is a quantity depending on properties in my approximation space Hn, and this quantity is basically how well solutions of the adjoint equation are approximated in this space. Okay, so let me write the definition up, and then we can talk about it. So I've got S star F minus Vn in the H1K norm, and I'm minimizing over elements Vn in the finite dimensional space, and I'm taking in the sup over all data F in L2. Okay, so in fact, this isn't so important. I'm going to circle this, and this is saying how well solutions of the adjoint equation are approximated in this space Hn. Okay, and by this lemma, this first lemma here, this is just how well solutions of the regular Helmholtz equation, okay? Equation are approximated at Hn. So if this quantity is sufficiently small, okay, relative to the continuity constant of the sesquilinear form that we know is some number or something independent of k, then I have this inequality that I want. Look at it, I'm going to be fancy dancy and copy it. Look at it. Some pro, if I do say so myself, some pro usage of good notes here. And therefore, I do then have my, what we showed on the previous slide was that then I do have quasi-optimality once I have this equation in black. So here I'm writing down the quasi-optimality bound once again. Right, so we're going to prove this lemma, but again, I want to sort of just emphasize, and it's related to these great questions Stephen was asking yesterday. It was so this lemma is great because this is now a question about approximation of some function that I know, right? Or at least I know information about, right? I've got my Helmholtz solution. You know, we're going to use information we have about the Helmholtz solution and then answer this approximation question, right? Given our Helmholtz solutions and the subspace, how well does the subspace approximate them? And then that's going to tell us actually how well the numerical method finds approximations to the solution. Right. So Igor, in principle, are you with me? Do you understand what's going on? Have you got any questions?
Yes, I'm happy.
You're happy? Okay, excellent. Okay, so now let's prove this lemma. I'm just rearranging my notes, but it has the added advantage of having a pause now to increase the tension as we prove this lemma. Okay, so because this is the sort of one numerical analysis kind of proof that we're going to do in this course, so I thought I'd pick it up a little bit. Right. Right, so just to recap, I want to prove now the L2 norm of the Galerkin error is less than a half the H1 norm. And somehow all the ingredients I've got, so the ingredients I've got is this definition of this adjoint solution operator. Oh, okay, I need to add a new, sorry, I need to add a new page here. There we go. So I start now with a square of the norm I want to bound, which is u minus un in L2. And now this is equal to a u minus un s star u minus un by this definition of s star, right? So in fact I'm going to repeat it, right? So remember a v s star f is vf for all v in h1, right? So I choose f. So I choose f to be u minus un, and then in particular I let this holds for all v. I let v be u minus un. Okay, so then this becomes my L2 norm squared of u minus un. Now, what's the other tool I have, right? I have Galerkin orthogonality, right? Because that involves a u minus un. It says when I have a of u minus un, I can then add to the second argument any finite element function, any function in my finite dimensional space. So this is now a u minus un s star u minus un minus vn for any vn in this space Hn by Galerkin orthogonality. And now, so now I've got this. I've got like this difference, which is again is saying how well, so because this is for all vn, so I can change vn, and this is then related to how well this adjoint solution operator is approximated in the finite element space. Now I use continuity to get now C cont, and I get the H1K norm of U minus UN, right? Because remember, I want to bound this L2 norm of the error by the H1 norm of the error. Okay, so one way I can get the H1 norm on the right-hand side is to use continuity. And then I have this S star U minus UN minus Vn H1K. And now, so the definition of eta, how this was defined. So let's actually let's copy it again. Copy, paste. Okay, let's put it here. So this is the definition of eta from before. This definition of eta implies that this is less than or equal to eta of Hn times then U minus Un in L2. Okay, because I'm letting U minus Un be F. So I'm choosing. So this thing here is less than or equal to eta for all F. So for this particular F of U minus Un, this quantity here is then less than or equal to eta U minus Un L2. And now you see, now then I cancel. So so now I can cancel a U minus Un L2 on both sides and get the inequality I want. Let's just write it out. So this implies U minus Un L2 is less than or equal to C cont eta of Hn, now U minus Un H1K. Right, and so the claim was, so I want I want the L2 norm to be less than or equal to half times the H1 norm. So if this is less than or equal to half, then I'm good. And so therefore need eta of Hn less than or equal to C cont over 2, which is the condition that we claimed, right? We said if eta is less than or equal to C cont over 2, then I have this inequality. That's what we've got. That's what we've got here. Kirill,
Yeah.
are you following?
I only have one issue here. So I can see that you have used the fact as the superable over F, but then there's a minimal inside.
Sorry. So yes. So sorry. So this is exactly. So the point. Yeah. Good. So the point is this is for all V in Hn. You see. So I can choose some V then. So yes. So that's by definition. Yeah. Good. Thank you. There exists a Vn in Hn such that this is less than or equal to.
Right. Okay.
Good. Excellent. Again, thank you, Kirill. I'll give you your fee afterwards for doing that. You know, that deliberate mistake on my part, deliberate kind of response. Good. It was just as we rehearsed. So good job there. Thank you. Do you have any non rehearsed, non-planted questions you'd like to ask me? About so is the rest of it clear? Sorry, that's what I'm asking.
So the goal was to prove U minus UM in L2 is less than or equal to 1/2, right?
Half this, yeah, half this guy, yeah.
Yeah, but you have C cont.
Shit. So good. Sorry. I mean, oh yeah, sorry. I've got the C cont in the wrong place. Sorry. Thank you. It should be. Sorry. Good. Okay, that was also good. Good. Sorry, that's a mistake then in my thing.
You know, on the previous C cont over 2. So in the previous level, on the previous slide, it should be also.
Yeah, this is also wrong. Thank you.
Sorry.
Thank you. Good. 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 Thank you. Excellent. It's great when the audience correct you. I'm obviously I'm not so happy I make mistakes, but I'm happy because it shows that you folks are following. So excellent. Right. So we've now, so as I said before, we've now reduced our question of finding sufficient conditions such that this Galerkin solution exists and satisfies K-independent quasi-optimality. We've reduced that problem to this question of approximation of Helmholtz solutions in this space Hn, right? In this piecewise polynomial space. So now I'm going to state some results about piecewise polynomial approximation theory. So if you've taken some like first course on numerical analysis of the finite element method, you will have seen this before. But even if you haven't, I'm hoping to relate it to things that you have seen before, or to argue that this is not so scary. So in this sort of first course on numerical analysis of the finite element method, you'll be introduced to these interpolation operators. So this is then some operator where IH of V is now in the space Hn, this piecewise polynomial approximation space. And these interpolation operators have the property, so let me write down this property and then we'll talk about it, that if you measure, so this is D is just some arbitrary domain, okay, well, we'll work, but so for us, we're working on this ball of radius r, but let me just write down d. This error then in this interpolation, so I take v, the error between v and its interpolant, measured in the HM norm, is just bounded by a constant h to the s minus m, then the hs semi-norm of v, and that this is valid if the polynomial degree is bigger than or equal to s minus 1. So now let's just do a simple example immediately to try and convince you that for those of you who haven't seen this before, this is not so unexpected. So for example, if I take m is 0, so I'm measuring the error in L2 here on the left. And if I assume my polynomial degree equals s minus 1, okay, so I've got some function with regularity hs, and my polynomial degree is equal to s minus 1. If I use, let's say, a Taylor series with s minus 1 terms on some element to approximate the solution, then the remainder, the Taylor series remainder, is like h to the s, and it's going to involve ds of v, right? And then you see that this in this setup is somehow our right hand side, because m here is 0, because I said I'm going to approximate here in the L2 norm, and this is then there. So I'm hoping that in this sort of simplest case, measuring error in the L2 norm, just by, and this is in fact how, well, the idea behind these simplest interpolants is to basically use some Taylor series type argument. Okay. Stephen, how are you doing?
Yeah, I just understood it as soon as right before you asked me.
Sorry, say that again.
Good.
Okay, good. Okay, so yeah.
Yeah, so this is very nice. In other words, Taylor series work, you use those kinds of polynomials, and you see that the error is going to be coming from the rest of term.
Okay, so I didn't hear all of that, but I'm going to assume you. Yeah, I think you were saying you understood what was going on.
Yeah.
Okay. Good. So now, of course, so this was using these unweighted norms in K, right? So we're going to weight things in weight norms in K, and also here I wasn't keeping track of this P dependence. So now I'm going to write down the result of basically if you sort of soup this up to do these weighted norms in K and keep track of the P dependence, but somehow so it's going to look a bit fancier. But the idea is basically the same as this. So it's that. So again, this smallest error in approximating a function v in this space, this piecewise polynomial space, measured in the H1K norm, and so this is really given a v in HS. This is bounded by some constant, say c approx. That depends on s, then times hk over p to the s minus 1, 1 plus hk over p, then k to the minus s, vs, this hs semi-norm. Again, this is if p is greater than or equal to s minus 1. Okay, oops. This now is kind of the analog of this. The difference is now I'm weighting with k. This creature here is now the analog of this. But again, these yellow things are somehow analogous. But again, I've got some weighted with k. And then here, yeah, okay. So I think this 1 plus hk over p is just because I've got I've got an L2 bit plus then a weighted H1 bit on the left-hand side. Okay, so we're going to take that on trust now, and now we're going to use this to obtain this result about the finite element method. When p is 1, the polynomial degree is 1, and I'm just decreasing h. And I said to you yesterday that this we get quasi-optimality when hk squared is sufficiently small. Now we're going to prove that. Okay, so we're going to prove that by bounding eta. Okay, so we're going to have a bound on eta. Okay, so remember.
Can I ask a question?
Yeah, please.
This is just so I follow what's coming. Am I supposed to see the effect of the pollution already in some of that stuff that you wrote?
No. So you should just think of this as just some fancy k-weighted version of this, right? So again, it's basically just Taylor's theorem, but it's just like I want a k to the minus s here, so I've got this k here, and I've got this, you know, I mean, yeah. So there's no kind of deep meaning to these weights to the k's appearing here.
Okay, so it's like a local thing, and what you're going to show us.
Yeah, exactly. This is still a local thing.
Okay, because I thought maybe I missed something in the interpolation operator that was not normal, but I guess not.
Well, yeah. So
maybe not.
Okay. No. So for continuous functions, this is really just this node. So the nodal interpolant, it's really a local thing, defined on each element.
Well, will you, as you go along, will you show us where the pollution comes in?
Sorry, say again.
As you go along, will you show us where the pollution comes in?
Yeah. So we're going to see it right now. So right now we're going to derive this condition. So it's a sufficient condition. But in fact, the numerical experiments show it sharp that you need hk squared small, right? So that's this pollution when p is 1. Okay. So good. So the bound on eta now. Okay. So remember. So let's write down our definition once more. Eta of hn was this sup of f in L2. Then okay, it was 1 over FL2, and then the smallest possible error I can incur in approximating S star F by elements of this space calligraphic H sub n. Okay, now we're going to use this. So we use this piecewise polynomial approximation result with, okay, p is 1 because we're using piecewise linear basis functions, and s is 2, okay, because somehow so p has to be bigger than s minus 1. So if I'm choosing p as 1, the highest regularity of my function I can use is 2, s is 2, and that's okay because I mean the Helmholtz solution, you know, with L2 data, L2 right hand side f, my Helmholtz solution is in H2, but it is no higher than H2, right? So I'm not leaving anything on the table here a priori. So we're going to apply this thing. Okay, so we've still got our sup. Let's write sup of f in L2.
What do you want on the right hand side of the previous inequality? Is it HSK or HS only?
Sorry, so this is hk to the s over p to the s minus 1.
Normal phi on the right hand side. The normal phi, is it HSK or
no? So here it's yeah. So it's because I didn't define the semi-norms with the weighting. So yeah. So sorry. So when I write this, I guess it's the semi-norm HSK, but it's just that I didn't define, you know, what the semi-norm was, right? But yeah, I mean, it's this is of course the natural weighted semi-norm. Okay. Okay, so now I'm going to use this bound, so I get a C. Oops, a daisy, wrong color. So I get a C approx. I get HK over P. Okay, so P is 1. So let's just, okay. P is 1, so I have HK, S is 2, so S minus 1 is just 1. I get then a 1 plus HK. And now I get a K, okay, get a K to the minus 2, this H2 semi-norm, S star F. Okay. But one of these things we recapped, so let's go back. I'm just going to go turn the slides back. So this thing we recapped on the first page was that the H2 norm of the Helmholtz solution is bounded, okay, in the weighted space by K times R times the L2 norm of F, right? So here now, okay, here we've got S star of F, but there was this lemma that said, hey, S star of F is just a complex conjugate of a regular Helmholtz solution, so I can use that bound. And so this thing here, let me do it in a different color. This is less than or equal to some constant, then K times R times FL2. Okay, that was that final piece of sort of knowledge about Helmholtz solution operator we're going to use. So therefore I get then, this is like C, okay, C approx, and some constant, HK times KR, then 1 plus HK. Okay, and so this then, okay, so when I was saying this condition HK squared sufficiently small, strictly this should be like HK squared R sufficiently small, because you know HK squared is not a dimensionless quantity. So then this being then sufficiently small is therefore the condition. All this sufficiently small is the condition, you know, HK squared sufficiently small. Okay, and so to answer sort of Stephen's question, the sort of pollution is coming from this bound on the solution. In fact, this is a good way to think about it. In fact, the pollution is coming from this bound on the solution operator here, right? Like making here we've got these factors HK. This is kind of what we expect. But then when I use when I bound this H2 norm of the solution, I get this K here, and that's causing then the condition to be HK squared sufficiently small.
Yeah, that makes sense.
Okay.
So that's like
Good. Look at it. People are even talking before I pick on them. There's some serious, you know, interaction going on here. I'm excited.
Well, you caused it. You made us quit.
So say again.
Oh, it's fine. You caused us to do it. Good job.
Okay, good. Right. So let's now. I'm going to go back to the first slide just to sort of recap where we are. So I've now given you this argument that says, okay, when P is 1, HK squared sufficiently small is a sufficient condition for, you know, this K independent quasi-optimality. But in fact, you know, then these numerical experiments I showed you the graph yesterday show that in fact they are somehow necessary, right? That this is the sharp threshold. Great. So now in this last sort of 10 minutes of this lecture, and then in tomorrow's lecture, we're going to do this fancier result, right? That says, okay, if I actually increase P logarithmically with K, I get no pollution. Right. So now we're going to state somehow the main theorem of this mini course. So let's go here. So this is theorem. And so like I said, this again exactly in this model problem case, this was proved, or for our model problem, this was proved by Marcus and Melenk and Stefan Zauter in 2010. I'm going to give you a different proof in this tomorrow. And what the idea is, okay, so in fact, here you see what is killing us here, or what is, okay, killing us is a strong word, sorry, rephrase, the origin of the pollution is this power of K, or factor of K times R, that's arising from bounding this H2 norm in terms of the data. Okay, but somehow this again, that is really there. That bound is sharp. So how are we going to get around this? So what we're going to do, what the solution, what Marcus and Stefan came up with is that they're going to split the solution. Okay, so the Helmholtz solution restricted to the ball of radius r is split into two parts. I'm going to call them UH2 and UA, curly A. Where, okay, and I should say, so I'm thinking about the Helmholtz solution. Of course, in this argument, we got these solutions to the adjoint equation, but solutions to the adjoint equation are just complex conjugates of regular Helmholtz solutions. Okay, so that's why I'm working with the regular Helmholtz solution here. Where, so UH2 is in H2. I mean, otherwise it'd be pretty terrible notation. But UH2 is in H2. And okay, so I'm going to put in these BRs just because this is the result. We're going to state it in all its glory. This now is bounded in terms of the data, but I've lost the KR, right? In fact, I'm going to write down here. I'm going to remind you. So recall, we just had it on the previous page. U in H, the Helmholtz solution itself is bounded by a constant times KR. Let me just write that looks like a function of KR. So CKR times FL2 BR. Right? So in particular, this is kind of comparing this. We see 1 power of K better, right? Or 1 power of KR, sorry, 1 power of KR better than the bound. So this UH2 satisfies a bound that's 1 power of KR better than the bound satisfied on the Helmholtz solution. And U calligraphic A, so in fact this function is analytic, and it satisfies these derivative bounds. Okay, so I'm gonna, because I want to be careful about constants, I'm going to have the bounds on the derivative, the alpha derivative, weighted by K, measured in L2. This now satisfies, let's say, C2, KR, and C3 to the mod alpha, F, L2, BR. And this is for all, okay, K greater than or equal to some K naught. So we choose some K naught. So we choose K naught greater than 0, just a bound away from 0, and then these constants C1, C2, and C3 depend on K naught, but they're independent of K. Right, and you see now, so this creature, this creature here, UA, has the same KR dependence, right? If I just put alpha is 0, this is saying that L2 or alpha is 2 even, this is exactly then the same bound here. But UA actually has got more regularity. It's C infinity. It's in fact analytic. You can show this implies this UA is analytic. So I've got the same KR dependence, but I can keep on. I've got more and more derivatives, and we'll see that that's going to help us. Okay. Right, and so I'm just pausing because and actually so this sort of splitting into a part with finite regularity, a sort of H2 part, as part with the same regularity as the Helmholtz solution, but 1 power of K better, and then an analytic part has the same K dependence, but has higher regularity. That this splitting is really the sort of heart of the theory, and that's what then both Marcus and Stefan and then myself and my collaborators who I showed you yesterday, we then gone off and proved, you know, these splittings, this sort of decomposition of Helmholtz solutions then in much more general cases than just this free space model problem. Right, so now let's see actually, so let's take this theorem. Okay, I should highlight this theorem because it's the main event. Let's see now, just at the end of this lecture, right? So I'm going to now spend the last 3 minutes showing you how this gives you the bound on eta to show that this HP finite element method doesn't suffer from the pollution effect. So you use the splitting to bound eta of Hn. So eta of Hn, so I can approximate U and UH, sorry, I can approximate UH2 and UA separately. By elements of the space. Right, and now, okay, this UH2 bound, this goes exactly as it did before, but now I've gained my power of Kr, which means I just get, this is bounded by some constant HK over P, right? Because, you know, I have basically, it's going to be HK over P, 1 plus HK over P. I have this factor here, but now this Kr is gone here, right? So in fact, let's be more precise here. This is HK over P, 1 plus HK over P. Okay, so here's where the benefit of UH2 having this 1 power of Kr better helps us, right? It means I've got rid of my Kr. And now one can show, so it's again, it's essentially using this piecewise polynomial approximation result I showed you, but being a bit more careful with the P dependence, the constants. So I'm sweeping that under the rug a little bit. One can show that this is smaller than Kr times then HK over some constant sigma P to the P. Right, so if you remember, my piecewise polynomial approximation result had these things, you know, HK over P to the S minus 1, and so here we've got sort of HK over P to the P, and the point is I can take P as large as I want, right? Because UA is in C infinity, I'm not restricted by the regularity, and then this factor here. So I've got this bad factor Kr, but I can get rid of it by taking P large, right? So this is small or sufficiently small if HK over P is sufficiently small to make this quantity here less than 1, and then if P grows logarithmically with K. So then this factor here kills, okay, it kills Kr. And in fact, I could replace this Kr with any polynomial, so with any with Kr to the M for some M. So this is the polynomial resolvent bound Stephen was asking me after last lecture. So I can have much worse dependence of the solution operator. I can have this, yeah, as I said, Kr to the M. And still, I can absorb that by this, then HK over P is sufficiently small and P greater than some constant times log K. Okay, so that then is this result. So it says, you know, so thanks to this splitting, I can show that these conditions, HK over P less than or equal to C1, P greater than or equal to C2 log K, then give me this eta sufficiently small, which then gives me this K independent course optimality. So that's, and then again, that's the statement that the HP finite element method doesn't suffer from the pollution effect. Right, and so tomorrow our last task is to prove this theorem in yellow. And that's where you folks are all going to be completely at home. So we've done all the hard stuff. you folks can be completely at home, because we're going to start off, we're going to be using Fourier transforms, just like Stephen was using in the last lecture. We're going to be using some nice, easy PDE theory, and you're going to see how to prove this. Okay, thank you very much. That's everything for today. But if you have any questions, you can ask me them now, or email me and I can address them before next lecture. And I'll stick these slides. So on my webpage, I've got the first set of slides or the first set of notes. I put these up there too. Okay, I'll stop talking.
Okay, thank you very much. Thank you, Johan. We have survived the second lecture, so
Good, excellent.
yeah,
I'll see.
well said for the final lecture tomorrow.
Good.
Yeah.
Okay, well, yeah, I'll let you have your coffee, but yeah, like I say, any questions, just let me know, and see you tomorrow.
See you tomorrow. Okay, thanks.